Hi everyone, my name is Andrzej Krzemieński, I work for Sabre, and I'm here to talk about error handling. This is something that affects practically every single programmer, something that I consider the most interesting aspect of programming, something that is very important, very easy to get wrong, and somehow neglected while teaching C++. To the extent, my experience when I finished the university, the only thing I got from C++ is that you need to use exceptions, but they cause memory leaks, they cause your application to terminate, and the best thing you can do when you are dealing with other people's libraries is to catch the exceptions as soon as possible and protect yourself against those dangers. For the record, I'm not really saying this, but this is my understanding. And I feel that this might be the understanding of other people also. So, the purpose of this talk is to give you, I don't know how this works, some model that helps understand what we are doing here, why we are giving advice that we are actually giving, and how to use it to your advantage rather than being a victim of it. And the first thing we need to do is probably to avoid using word error at all, because it has overloaded meaning, and in a common speech, when we use it, it means something else that we would want it to mean. Error, we think of it, means something like making the wrong choice, or deviating from the truth, or making a mistake, and this is not what we are doing here. So instead, we would use two different words to mean two different things. One is a bug, and this is when the programmer has typed something else than he intended to type. And the other is failure. This is when the program does exactly what we wanted it to do, but it encounters some hostile situation in the environment, and it has to react. So to go into some more detail, this is how a bug looks like, in case you didn't know. I try to compute a distance of some point from the origin, so I first multiply, then I square root, and I get the distance, but in fact I don't, because there was some other variable called very similarly, and I typed that one instead. Because they have the same type, it just compiles, does something, probably not what you want. And the characteristics of the bug is that programmer has caused this, and the correct response to observing a bug is for the programmer to go back to the code and fix it. And the tools to do that would be like static analysis, and we have features in the language that can help the static analysis detect this bug, like type system. If B and D were different types, I would get a compiler error. There would be no harm. I would work before I even compile the code. Contracts. We were supposed to get them in C++ 20, now we don't, but the contracts are still there conceptually. If there was a way to say that the square root never gets negative numbers, the static analyzer could detect that there is a path that gives me a negative number and could warn me. This is also possible to detect it at runtime, but there is no good corrective action to do because the programmer cannot respond like that, so whatever we do is suboptimal. Anyway, so we will not be discussing those bugs anymore. We had good talks about this in CppCon. We will focus on the other ones, which is failure. Failure is something that is caused by the environment, so we cannot predict it. We can predict that they will happen, but we don't know if they actually happen, so there is a way to protect statically, and the correct response for the program when it encounters one is to take a different branch in the code. So every function like this, we have open a socket, we call it open a socket, but what we really mean, it either opens the socket or reports failure. this way or another. But it's always this either or. And if it's this positive path, we call it a post condition. We say that we did what we promised, otherwise we need to report failure. And this implies that there will be branches in the code, or in the code that is calling us. We handle two different situations here. So let's start with some real code. This is a hello world for writing a HTTP client in C. I changed it a bit so it's C++-like, but I have the error handling intact. So what it does, in short, it tries to open a socket. If it works, it tries to resolve the host name. If it works, it tries to connect to the server. If that works, it writes some data to the server. If this succeeded, we retrieve some data from the server back. And if that worked, we output the data. And maybe you cannot see it from the back because it's small, but it's even better because the point here, the only point I showed in the slide is that there is a certain pattern here that you can observe. We have all those if statements that deal with the extra branches we take in the code. And the pattern in general is this one. We try to open the socket, we check if it failed. If it failed, we die. The die may seem like confusing and scary, but the point, at least at this point of all this talk, we'll refine it, is that we express some dependency between the operations. Like, we don't want to go resolve host unless OpenSocket succeeds. This could technically work, but there's no point in doing this because we will not be doing subsequent operations anyway. And if the resolve host fails, it's not only that we don't want to connect. If we tried it, we probably have a bug in our code because function connect probably has a precondition. It requires that we have a socket, we have a host to connect. Maybe it could report a failure on its own, but maybe it's not prepared to handle this. Maybe it trusts us that we did it. So it may cause random things in our program, because UB crashes random results, we don't know. So you want to try to avoid it. And this is the whole point of error handling. You want to avoid the operations. You don't want to call operations if the previous ones fail to depend on it. And so if OpenSocket fails, there is no point in doing other operations. We have to cancel them. And this whole thing is part of another function, like get data from server. So it didn't work either. It has to be cancelled, entire operation, and whoever depended on it, if somebody wanted to get this data and transform it, it also needs to be cancelled because there is no data. We can't output it anymore, we have to cancel this, and we cancel next operations and next operations until we are sure we have cancelled everyone that depends on us. Of course. Now, to die means output some string and exit. And it is a correct way to do it in some applications, like if you have a small application like this one, you just want to get some data and be done. If we cannot connect to the server, there's nothing else we can do. We might as well terminate the entire program. But normally, this is a server, it has to process a lot of transactions, and we won't fail for some tiny reason we won't be killing it. So this has to be more subtle. But there is certain risk. If we try to stop this, we will execute the next operation. And if next operation depends on the previous ones, we get it back. So when we start this cancellation cascade, we need to be sure that the next operation does not depend on the previous one completed successfully. And there is not much places like this in the code where this is the case. But there are some, like for redundancy, we may try to get data from 3 servers. if getting data from one server fails, it may still be okay because we have the other server that will give us the data. So this is not our failure. Or another typical situation in a server's main loop, when we process one transaction and it fails, it doesn't stop us, we can cancel the entire transaction. This is how it looks like. We process the next request from the queue, it may fail for whatever reason, but it doesn't stop us from moving on. We just send some apology message to our requester, and then we move on to the next instruction. It's likely that the next one succeeds because it takes different paths. The situation in the environment may change. We may have more resources. We can move on. And in order not to kill the program, we need to do something more subtle, like use an error. And I'm showing you the error codes not because I prefer them or I want you to prefer them. I use exceptions in my program, but this is to illustrate that what we are talking here, this success dependency, works for any failure handling techniques that I know. For exceptions, error codes, with outcome, if you like it, error monad in functional languages, it's all the same about cancelling dependent operations. So this is how an error code looks like. Status is something that at minimum has a true-false indication whether we succeeded or failed, and if any operation failed, like open a socket, we do a premature return and indicate a failure, so our callers can also cancel their operations. And if everything succeeds, we return the success. And the only way the exceptions differ here is in ergonomy, because this pattern of check if it failed and do a premature return is so pervasive in the programs that we may as well optimize the code for it. So in case of exceptions, if everything is reported, the exceptions we just express the operations, and only because the connect is below OpenSocket, it immediately means that it will get cancelled when OpenSocket reports a failure. Or let's go back. So it chooses different defaults. If you don't do anything, just if you state your instructions, in case of exceptions, it means they adhere to this success dependency relation. Whereas in error codes, if you do nothing by default, you get no dependency and you get probably a bug. So another reason for preferring exceptions to error codes, at least in the past, was that it's very easy if you are thinking positively to forget to type the if statement and get it into a bug. But it is no longer the case in C++70 because we got no discard. And if we annotate our status with no discard, it means whatever function returns this type and you forget to check it, to read it, the compiler must give you a warning. And if you turn warnings into errors, and you get the error, you are stopped, the compilation is stopped, you have to make a decision to make the program compile. So the exceptions make a good default, which is 95% of the cases is the correct default. But if it's a compiler error, it's probably even better because you are forced to make a decision. And this is not to convince you that error codes are any better, it is to show you that the balance of the arguments have changed since C++17. Now, let's make it a bit more strict. We open the socket, we need to close it. But if we do it like this, in case any operation in between fails, we are skipping the closing of the socket. And this is a general pattern that also occurs very frequently, that when we are dealing with resources, it is simple dependency, the success relation will not work. So resource, if we were to provide a definition that is relevant to us, is something that we are short of. And we need to share with others, possibly with ourselves later. And resource is like a goal, it's always there. But what we need locally is to tell the system that or tell the other potential owners that we own it for this amount of time, we are exclusive owners. So there is a concept of possession with the resource. When we acquire our resource, we say we want to be exclusive owners of this resource. And when we are done, we are telling the system that others can have it now. So we're leasing the resource. And our dependency graph, the success dependency, looks different when we're talking about the resources. So any operation that uses the socket depends on it. Our closing of the socket also depends on our opening the socket being successful, but our closing the socket does not depend on the other operations failing in between. And C++ has a tool to address exactly this use pattern, and this is called deterministic automatic object lifetime. If you create an automatic object, you know precisely when its lifetime starts and when it ends, and you are guaranteed that the constructor is called when the object lifetime starts and the destructor at the end of the lifetime. And this exactly maps on starting and ending a session with the resource. If you acquire a resource in a constructor, and you release the resource in the destructor, you have mapped the object lifetime onto a session with the resource. And the destructor is involved no matter how we exit the scope, whether it's a premature return, whether it's an exception or a normal return. Which also illustrates that RAII, what that is called, is useful not only because we have exceptions and we have to protect against them, but it's also useful for any other technique or for handling failures. Now, an interesting question is it possible that we fail to open the socket? And the answer is yes, we're talking to the system. Different things can happen. It's possible that we will not make to release the resource. But the more important question is, do our callers need to know about it? Because we need to use the resources to do something, but using resources itself is hardly ever our goal. We need to manage the resource, but our contract with the callers is we need to provide some data or change the global state. And this is what our callers care about. To some extent, they need to know it's C++, we need to reason about the performance, so they have to know that we are doing something inside, but they don't need to be cancelled in case our releasing of the resource fails. Let's see what it means in the code. I need a socket, so I create it. If it fails, there will be no data to get to our caller. I need to cancel our caller. This is the point of reporting failures. Same here. I cannot connect, there will be no data. I cannot obtain data for other reason, no data to return. But here, I have data to return. My caller can transform it, can do whatever it wants with it. I may fail to close the socket, but there is no reason to cancel my caller. He can do his job. My post condition is satisfied. I left some mess behind, sorry, but there is no need to cancel anyone down. Maybe you want to report it somehow, maybe you want to log it, maybe you want to set some global flag, but you are not canceling the callers. Because reporting failures is not about broadcasting any information about something you don't like in the environment. It is about saying who gets cancelled when you fail. So to complete our graph, our dependency graph, closing of the socket depends only on successfully opening the socket, and further usage of our data does not depend on our closing of the socket completing successfully or not. That is, I'm not encouraging you to leak resources. But we tried. If we fail, there's nothing else we can do. So we are sometimes talking about if you throw it from the destructor, you can get double exceptions. It's all true, but you never get to this point if you adhere to the rules. The reason we don't want to throw from destructors is because this doesn't fit into the conceptual model of a resource. So our goal here is, because it's not always obvious, to identify those patterns. If you can see in the code that this releasing something does not disturb the other operator, failing to do something does not depend on other operations, you have probably identified a resource in your code, and you probably need to apply this RAII. Yeah. So another question is, okay, I use destructors for releasing resources, can I use it for anything else? Like, I have a class that represents a transaction with a database, I put some operations in it, now maybe I want to commit the data in the destructor, because it's so obvious that I will be doing the commit in the end that I don't even want my users to type it. And the answer is, yes, of course, it's a free country, you can do whatever you want, but the language has not been designed to handle this situation. So you will be working against the mechanics of the language, and the mechanics of the language will work against you. So you need something like this on the left-hand side, the normal, straight success dependency, except that the commit is invisible. But it should work the same way, but you will get something else. Because the commit will be invoked regardless if the field record fails or not. We would like to not to commit data. If we don't have the data to commit, we will be committing it anyway. So you can think of emulating this. Like, first of all, the destructors, compiler annotates it as no except, even if you don't want it. So we have to make sure that you are actually throwing exceptions from destructors, because now the commit record is a normal operation you can hide. There is no way to detect. You would need to manually implement this additional arrow that we don't have, and somehow detect whether we are stuck on line or not, where the previous operation failed. And this is impossible in general. We have function Uncaught Exception, which works, but it doesn't actually work because you may have, because whether you know it or not, each thread of execution can have a number of exceptions being handled, and sometimes you have an exception that you handle, but you are not unwinding the stack because you started winding it back in some destructor, and it will not detect this situation. Since C++17 we have Uncaught Exceptions, so you can use it to count the number of active exceptions in the constructor and then in destructor and compare them. And it works, even though it's expensive, but it doesn't work in C++20 anymore because we have coroutines. So it's possible that we started with the object in one thread and the coroutine was suspended, resumed in another thread, now you will be counting exceptions from another thread. It will not work. And another thing worth mentioning here is logging, which also doesn't fit into the normal success dependency, because we want to cancel a log when some operation failed, we don't want to do subsequent logging, but when logging fails, unless we are in a special environment where tracing human actions is so important that we would rather kill the application than let it go unlogged. Unless we are in this situation, if the logging fails, there is no reason to cancel the subsequent operation. So good logging frameworks never throw exceptions themselves. If they need to report failure, they will just call some callback, but the program will not log. And now there are some implications of this success dependency model. Our cancellation cascade, when it starts, it will unwind the scopes, destroy objects that are in those scopes, and ideally it will do nothing else. And what this requires of us is to be sure that any object can be safely destroyed. Safely, here means that we get no UV, no inadvertent memory leaks. That's about it. And basically, we do not have to guarantee anything anymore. And what do I mean by that? Suppose we have something like a person in our code base. We'll be using those persons in many places, and many of our coders will depend on the fact that this person, represented by first and last name, represents a real person that we have somewhere in the database. Now, the assignment, which will be probably implicitly generated, will look something like this. First assign the first name, assign the last name, we're done. But should the second assignment fail for some reason, we will get in a place where the first name is new, but the last name of the guy is old. So we invented a new person that probably doesn't exist and may spoil somebody else's code. And the question is, what should we do in this class to prevent that? And the answer is, we probably don't need to do anything about it. Because in what situation will such a thing be observed? Here is a possible code that uses our person. We have some function process that has a precondition. It requires that at this point this person represents really somebody that exists in our database. We create a person. Suppose the next person always gives us a good person that exists. We process it. The first process is fine. The second, now we do the second assignment. We change a person to another. It fails. It creates a person that does not exist. But the other function process will never see it because it's cancelled. So there is no harm done to it. The distractor will see it. So we need to be sure that the distractor knows how to handle this situation. But if we are only releasing resources, that's fine. It's just two strings, two memory buffers, we will just release them. We would observe this that person if we did something like this. I'm putting a try at a random place. If I put it in the wrong place, I usually don't know once I caught it what to do with it, so I have to type / to do handle it later, which means ignore action, and then the process can see that person. But the problem here is not how the person is designed, but how you catch exceptions. If you solve the cancellation cascade, pretty much this is what you get. So you had better rather not do this and leave the person as it is. But if you are an observant student, you will notice that I disregarded my advice myself in one of the initial slides, because in the server example, I have a queue which will survive the stack unwinding, the cancellation cascade, and live longer. And this is true. There are some objects that need to survive the cancellation cascade, and for this object, you have to guarantee more than that. Maybe that if they fail, their state is unchanged, maybe that their state is reset, something more. But there are special objects, and for those objects, we need to apply special rules for which we will pay at runtime, because this is additional operations to be done. But there is not many of those operations, and we will leave this subject aside. There is another one here that also survives the cancellation cascade. This is the request. We are using it in function process, and if it fails, we don't know what happens. We catch the exception, and we are still using it when reporting failed. But this time, this object is constant, and this changes a lot. Because this is not a reference to a constant, this is really a constant object. So whatever state state it was initially, it would be the same state at the end. So if the initial state was correct, we have to assume that it was, it did not change. So the constant objects are really useful. This is where you appreciate that things are constant, because we don't need to talk about those failure safety guarantees anymore. Only because it's constant, you are guaranteed that it's in a good state when something bad happens. And this is another important observation here, that when we talk about failure safety guarantees or exception safety guarantees, we really talk about mutating operations. If they don't mutate, we know what state they leave the objects in. Now, going back to our person, there is another situation where we would observe a bad person. This is where we use a scope guard. I create a person which is good initially, then in the scope guard I'm saying that this lambda, this callback will be executed at the end of the scope. Now I'm doing the second assignment, and it fails, and the destructor is called of the scope guard, and it sees and it calls process sees the bad person. But again, this is not a problem with how the person is designed, but that you are doing in the destructor things that are not releasing resources. Now you are doing some logic in the destructor, and you are responsible for it. So the scope guards look cool, but they are also very dangerous. They are inferior to normal destructors because the destructor only sees the members of the class, and this is the only thing it can fiddle with. Whereas the scope guard like this can touch anything it has in scope, and it has the potential to break things. This is one thing that can break. There are more. We will not discuss them, and they should be used with caution. And thus we arrive at the definition of a basic failure safety guarantee. You may know it under the basic exception safety, but it really doesn't apply to exceptions alone. It applies to any failure technique based on cancelling operations that you can think of. So the two things to observe here is when any function fails, it cannot leak resources. But we've seen that sometimes it's inevitable, so we may be forced to leak something, but the point here is that we do not try to move this responsibility on our callers. If we are allocating anything, we need to, or acquiring anything, because it doesn't have to be more, we are also taking care of listening. It's our responsibility, our callers don't have to know about it. And the second one, when this function is a member function, it needs to leave the object in a state where it can be safely destroyed. Actually, in C++, we have an additional requirement here that whenever a member operation fails, its invariants are preserved, which is another way of saying that the object is in a valid but a specified state. Valid in the sense we define what is valid. We declare for every type what its invariant is, and we are saying that whatever happens, this invariant was preserved. So in our case of a person, the fact that it represents a good person, even though it's important to other people, is not part of its invariant. Another way of saying this is that any operation that doesn't have an explicit precondition on it can be safely invoked after an imitating operation fails. Safely means no resources are leaked, no UV, basic safety guarantee. So 2 points here is that this basic failure safety, again, applies to any technique of handling failures, and its main point is to enable this cancellation cascade to work correctly. And there are other implications of this model, like if we go back to the server example, if we cancel the operations, it's usually a long distance from the point where the exception or the failure was reported to the place where it is being, the cancellation cascade is being stopped, and and the failure reported. So the function process could have failed for thousands of reasons. It could report it through hundreds of exception types, but we will not be putting 100 catch statements here. We will probably want to catch them generically in one place. And if we do it, what information can we extract from such an error object in a generic way? This is not much we can do that. We could get some error number, maybe the name of the library that it originated from, maybe a short text that we could either display to the customer or log, maybe some indication at which level to stop the cancellation cascade if we have more than one. But one thing we don't need is this rich type hierarchy with virtual functions where every type can store arbitrary information different than the other one. When handling this generically, there is no way we can use it, but we will pay the cost of it. And that's it as it comes to describing the model, and hopefully it helps us answer the question that we usually have when developing programs and making decisions. Like if you ever ask yourself, should I catch the exception here? The real question should be, do the operations down below depend on the one that failed? Because if they do, it means you promised something in a post condition, you are not fulfilling the promise, the other people depend on it, they need to be cancelled, otherwise you will have a bug. So yes, or rather no, you don't catch exception here. Should I throw an exception here? The real question is, do our callers need to be cancelled? If they do, then yes, you throw the exception. Should I throw from my destructor here? The question to you is, are you using destructors for something other than releasing resources? And if you do, are you sure you are doing it correctly? Because it's very easy to get it incorrect. But if you do, if you know what the consequences are, if you make sure that you are really manually implementing a normal, straight sector dependency, then your operation in the destructor is a normal operation, except that it's invisible. And you do throw exception, because you want to cancel subsequent operations that depend. But what if nobody catches my exception and my program terminates? Well, there are two cases here. Maybe this is what you want. Maybe everyone down below depends on your operation. There is nothing else the program can do, and you need to shut it down. But the other possibility is that you are afraid that somebody could have stopped the cancellation cascade and should have, but they forgot to type a catch statement or something like this in the code. This is possible, but this is the problem in the caller. He has a bug. Probably this is not the only problem we have now, and he needs to be fixed. And you need to report the failure. But what if my caller is not exception safe? Well, what do you mean by being exception safe? Does it mean it doesn't care whether the operation fails and just calls at random next operations? It doesn't adhere to this success dependency? If this is the case, we have a more serious problem here that we will not fix locally by throwing or not throwing the exception. There's something that needs to be fixed in the caller or in the mess. But maybe what you mean is that your caller is using a different failure handling technique. Maybe you throw exceptions here, and this guy is using error codes for some reason. It's possible. In that case, we are switching from one error handling model to another. Yes, we cannot throw anymore. We have to adapt to our caller and check it probably to error code or whatever it's using. Next. What if throwing an exception incurs an unacceptable cost? Well, it's easy to get that wrong. Often these statements are based on intuition and not facts. You need to be sure that this is really the case, because often exceptions can outperform other ways of handling failures. But maybe you are right. Maybe you are in the environment, like low latency programs, where you are not interested in the performance of the positive path, but of the worst case scenario. Or maybe for security reasons, you want the positive path and the negative path to have the same time in order not to expose the information. Then yes, maybe exceptions are not for you, and you need to use other type of handling failure that is adequate to what you're doing. And I think we're done. To sum this up, the failure handling is about observing this success dependency, and in particular, not trying to stop the cancellation cascade at random places prematurely. We need to observe this resource handling patterns, and if we find one, we should use the RAII for managing this. We need to observe basic failure safety in order for the cancellation cascade to work. And whatever we say here applies to every failure handling technique there is. And I'm done talking. Thanks for listening. And if there's any questions or comments, I can take them. Just to have.
So I'm not sure how much it changes the story, but in the case where I guess it was the copy constructor person might fail, and you said, okay, well, we can have a precondition in process that says it's valid, and then we're okay. I mean, so to me, my intuition would be like, okay, that's not the way I want to do it, because now I'm paying the cost to validate this person every single time I make this call, so I would really want to do it when I do that assignment. Does that change the story, or what's your reaction to that?
So, I'm not sure if I got the question correctly. We are doing the copy constructor. This can fail. We need to report it somehow. If it's exceptions, it's easy, and you have this strong invariant. You know that when the object exists, it has the resources, it really represents something. And I think what you are asking, if we are not using exceptions, we have this problem of dealing with additional state where there is an object, but it doesn't represent anything. Is that the question?
So if you bring up your slide, let's see here. Right, so you say that fails. So, okay, yeah, if that throws an exception, fine, but I guess what I heard you say was that you don't care because you're going to validate it as a precondition of process. So this might lead to something invalid, but you don't care here because you're going to check it later.
Actually, okay. So the remark or the question here is that by recommending what I do here, I move the responsibility for checking if everything is okay on other people down in the pipeline. So my response to it is, I don't think I'm doing this because I believe that when this assignment starts the cancellation cascade, it's canceling every operation that could potentially see this object. There is nobody there down in the pipe that would even need to validate it because they all get cancelled, provided that I trust that no one stops the cancellation cascade and my objects are destroyed.
Yeah, so I agree with that, but I think if you go to the next slide, or maybe the one after that, so precondition P is existing person. So you don't know that. To me, if it's a precondition, I mean, are you saying it's a check precondition or an assumed precondition?
The way I see preconditions, it's always assumed.
Okay.
Then, not in the sense that you do optimizations, but in the sense that you are expressing what will be true.
Okay.
So there's two function processes. The first one, I'm confident that it is right because there was no exception being reported so far. I'm confident that the second one will never see that person because I'm confident the operation will be cancelled.
Okay. Thank you.
Hi. I have a question on your cancellation cascade where you say in the destructor, those mixed messages of in the destructor not to throw an exception, but you could throw it if you kind of knew what you were doing. It always seems a bad idea to throw an exception in a destructor.
Okay, so the remark here is that I sometimes say that you don't throw exceptions from destructors, sometimes I do. And if that, it's uncomfortable to hear that, yeah, you can throw exceptions. So maybe I didn't express it clearly. My recommendation is to use destructors only for releasing resources. And if you follow this, from that, it follows that you never throw exceptions from the destructor.
Right, your only post-condition is that you destroy the object, right? That's really all you want to guarantee. So you can't really fail to do that.
I can fail in the sense that some resources will get leaked.
But not in destroying the object. Yes.
I will leave it to myself.
So you would say really never throw an exception in the destructor. Would that be too strong?
It would be okay for me. I know it's not okay for people who want to use destructors for this clever completion logic.
I've never come across it in real code. That's why I ask.
Or let's put it this way: if you forget about doing destructors for clever things like auto-completion, you just never throw from destructors the end of the story.
Okay.
What about having a way to mark destructor as no exception? You have an exception in a destructor, if something very bad, something that never happens, you just abort.
So the comment is, what if something happens that bad that my program cannot probably continue because I'm not prepared for handling failures from destructors. And I think you answer it yourself. Yeah, then probably you want to terminate the program because you don't know what my program is not. The other parts are not prepared for this.
Of course, I'm talking about a back-end application. I would not do with something human, an exception that happens. Also, when you have an exception on a copy constructor, in this case, the case that you show is very good because, for what I'm aware, copy string can have an exception only if you don't have memory, that allows an exception. And this is another very, very bad condition. It's not like I cannot open a file. It means that if I don't have it now, it will have it by itself very soon because everything has allocated. So I tend to classify exception in several clusters. That's my point. And some of them I do just abort. Other I will handle. So that's my point of view.
Yeah, so the comment here is that there are situations that you can anticipate. There will be no way of handling them in the program. Yeah, and you terminate it immediately. Like,
on one of the slides, you say that basic value safety assumes no resource leaks. I would like to shortly argue about it. For example, if you, in one of internal functions, you created a file, opened the stream, then you have an exception, of course, well, the stream will be closed. But empty file or partially created file, it's still a resource leak, it's some resource, kind of. So actually, and when I formally read definition of basic exception guarantee, I see that from CPP reference, the program is in a valid state, but it may require cleanup. So I would say that if a program requires cleanup, you have a leak. So I disagree that no resource leaked is a part of basic failure safety.
Okay, so the comment is that
the comment is basic failure safety does not assume that you don't have any leaked resources.
So that there is a other definition of, because I have to repeat the question, that there is a other definition of basic failure safety guarantee, which suggests that you may need to clean up the resources yourself. Is that?
Oh, well, I think it's not as a definition, it's kind of main definition read directly from cppreference.com, kind of I would say.
This is the definition read from cppreference.com.
Could you comment?
My comment on this is, if this is really the case, then I disagree with the definition in cppreference.com. And the way I understand basic failure safety guarantee is that, yes, it's possible that I will leak the resource because there is no way to do that. If I want to close a file on a remote machine and I drop the connection, there is no way I will do it. But this responsibility will never be pushed on my callers. My callers needs to be written. I mean, this relieves my callers from this responsibility. And this is the advantage we get from this guarantee compared to, I've worked on libraries like this where they would say, you get this if you get some connection, you get a connection, but if it throws an exception, then you have to call release, unless this is exception of type something, in which case you don't have to release. You don't have it with basic failure safety guarantee because the border, the contract is the caller does not need to care about releasing the resources. You need to care about it. Ideally, you close it. In some situations, you may not, but it's legal.
Yeah, hi. Question for you and really for everybody else here. Handling out-of-memory situations, right? You call new and it throws an exception. We're all told, well, you have to catch the exception. I've got a legacy code base, very, very legacy code base. It's got mallocs everywhere, right? Only a fraction of them actually check to see if it's a null pointer coming back. I'm claiming that I'm not going to worry about that. I've got bigger problems. Because if we're out of memory, it's running on a Linux machine, you're going down anyway. So my question for you and for anybody else, has anyone ever actually seen a case of handling an out-of-memory error and doing something useful? I suspect this is very rare or maybe impossible, but I would really like to know.
Thank you for this question.
I would really like to know about this.
So the question is whether it makes sense to even handle out-of-memory errors returned from alloc or new, given that it's so pervasive everywhere in the code, and it's most likely you are not handling it anyway in other places, and there is nothing meaningful you can do. I have a use case in my company where I think we are handling this, but we make clear distinction. If operator knew, because first of all, I think it's a good strategy for handling this type of error to just ignore it. I think it's fine. You will just, maybe it will terminate your program, maybe it will be terminated at a different point. It's fine because probably you are not prepared for it. But I think we are, and this is because we distinguish that new can throw back alloc, not because it has run out of memory, but for other reasons. Like in the system you set the limit per single allocation, that it cannot be more than some memory, and my server is triggered by the customer request to allocate unusually big chunk of data. It cannot be processed, but there is still lots of memory there. Next request will succeed. So in this case, we are good with just letting the exception go. We catch it, we even allocate memory while handling the exception, and it's fine because we have plenty of memory still.
Good. Thank you. That was very useful. Thank you.
So we have a use case. So we work on robots which are autonomous. So having a robot crash is actually much worse than a robot not finish its tasks. So one of the things we do is we try to predict how much memory is remaining. And if you're getting close to a limit where we might be running out of memory soon, we'd either cancel the operation and go back to like the docking station charge, rather continue doing its operation. So it's a way of preventing that situation to happen, which is a rare situation, but having a robot crash and stop somewhere random place in a house is worse than in finishing its job. That's something we do.
So the comment here was that in other situations, you would probably have a custom allocator which monitors how much memory you have. And in advance, you have to somehow cancel the operations rather than letting out of memory. And this you probably reported via Badal or other exceptions.
It's a bare metal system, so we know how much we use.
Other examples I've seen is dump some kind of status output and then crash, or notice that you're out of memory, reset the system for a restart.
So if I understood the comment, you would, if you want a premature exit from the program, you want some additional logging to be done, so you
Yes.
don't know, you
Of
know
course,
what
you have to
happened.
be very careful about that. But log and terminate is one use case I've seen, and reset the system to some kind of initial state is another.
Yes, or if I can expand on this comment, if we terminate, in the sense that we call to terminate, it's not the end of our program. We still can do things to terminate, and what we do is schedule our application to be restarted, for instance. So the program, even technically, is ending. It will be restarted. So in a sense, it will be still in operation.
What you can't do is to keep the state, right? You have to do
That's
everything
a
at the start.
question about running out of memory. Many years ago, worked in a system, I remember what they did. There was pre-allocate like 1 megabytes of memory, then install a new handler. When you get this out of memory, you just release that 1 megabyte of memory, then you have 1 megabyte of memory to work with to do a
Yeah, just to report. Yeah,
That's
don't
nice
use
too.
any dynamic memory.
Exactly, I like
this.
that. Yeah, exactly. The other one, I've seen some embedded systems, though not recently, where you run out of memory. Means you've run out of memory in this physical memory bank, and you can actually switch to another bank. But I have not seen that one for a long time.
Yes, and paraphrasing the comment, I think somebody else once said that they work in an environment where you have 2 heaps. And if you're running out of one, you still have the second one to work with.
For example, the complete legitimate usage of the out of memory. When you work with the volumetric data, normally the volumetric data is at high res, and your algorithm just consumes tons of memory. And it's just saying, in a very normal scenario, your geometric model is too big, but the resolution you want, there is no way to do this operation. So try something different. And this is absolutely okay scenario. And when you catch this exception, that literally means that the buffer is already cleaned and you already gained back your memory. Just try something else.
Yes, so the comment boils down to if you are just doing stack unwinding, you are releasing memory, and only because of that, maybe the next operation that needs memory will succeed because you reclaim some memory back.
In our service, we have something very similar. If there's a parachute, if there is kind of memory, we do another strategy where we split more nodes in the cloud. We put things lower, and we are reading like one, so it is lower, but at least the customer has its own problem. The service put it. We are just very aggressive and sometimes we end up. And this pays off. Because we are in a multi-process environment, so everything is value calculated at the process, at the container, so the things are, it just works.
Okay, so we somehow switched the subject to handling Batala. We need to stop there because we are out of time. Thanks a lot for listening.